start recording. Okay. Okay, so we have that. Don't know why I clicked it. I don't see the chat. Okay, so other convergence tests. So there are other convergence tests. One of them is called alternating series test. Okay, but first we have to talk about what an alternating series is. This is a definition. An alternating series is a series whose terms are alternately positive and negative. Okay, so if you have a series whose terms alternate between positive and negative, positive, negative, positive, negative, or negative, positive, negative, positive, that's called an alternating series. You add those terms. Okay. Okay, so here are two examples. So one example is just the series 1/2 minus 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus dot, dot, dot. So see how the terms alternate between positive and negative. I'm just moving this so it's not next to the bullet point one there. Okay. So the first term is 1 minus 1/2, then 1/3, then minus 1/4. That's one example. Okay. But in that one, it starts out positive. You can also start out negative. So you have negative 1/2 plus 2/3 minus 3/4 plus 4/5 minus 5/6 plus dot, dot, dot. Okay, so you start out negative and you alternate. Okay, so here's another series that's an alternating series. Okay, so from the examples, you can see that the nth term of an alternating series is of the form. It's one of two possibilities. Either the nth term is equal to -1 to the let's say the n minus first term power times b sub n, or a sub n is of the form -1. Instead of to the n minus first power, you could say it's to the nth power, b sub n. Okay. Where b sub n is a positive number, where b sub n is a positive number for n. Okay. Note here, in this context, b sub n, the nth term of b is equal to the absolute value of the nth term of a, right? B sub n is the absolute value of a sub n. So if you have the terms of your series that you're adding, if you look at the nth term a sub n of this series, it's negative, it's plus or minus the positive, the absolute value of the terms, right? So the first term is 1, a sub 1 is 1. You could express it as -1 to the 0 times 1. So the terms, the b sub n terms here and here would be the terms 1, 1/2, 1/3, 1/4, 1/5, 1/6, right? Those would be the b sub n's. And then powers of -1 would just be adding or not adding a minus sign. Okay? So you can think of the terms of an alternating series as being negative, either multiplying by -1 or not multiplying by -1 times the positive values of the series. Okay. Okay, so that is an alternating series and a way to represent it in these forms. And so that leads us to the alternating series test. If the alternating series, which is the sum from n equals 1 to infinity of -1 to the n minus 1 of b sub n, this is equal to, so if this alternating series, which is b1 minus b2 plus b3 minus b4 plus dot dot dot, is positive, satisfies one, that b sub n plus 1 is less than or equal to b sub n for all n. And b, the second thing, is that the limit as n approaches infinity of b sub n is 0, and the series is convergent. Okay, so this is called the alternating series test. Okay, so if the alternating series of this form is the entire sum is positive, and the terms, the b sub n's are decreasing, right? B sub n plus 1 is less or equal to b sub n for all n. That means that b sub 2 would be less or equal to b sub 1. B sub 3 would be less or equal to b sub 2, which would be less or equal to b sub 1. So each next term is at most the previous term. So the terms are the b sub n's are decreasing. Okay. So one condition is that the b sub n's are decreasing. The second condition is that the limit of the b sub n's is 0. Okay. So if the b sub n terms are decreasing and the limit of b sub n is 0, then the entire alternating series sum is convergent. That's the alternating series test. Okay. So to use the alternating series test, following. Okay, so if one, you have an alternating series. Two, the b sub the entire sum is positive. Three, the b sub n terms are decreasing. And 4, the limit of the b sub n terms is 0, then the series converges. Okay? Okay, then the series converges. So if all 4 of these things happen, then the conclusion of the alternating series test is that the series converges. If you have an alternating series, if the entire sum is positive, if the b sub n terms are decreasing, and if the limit of the b sub n terms is 0, then the series converges. That's the alternating series test. Okay, so you can just follow that. These 4 things hold true. Apply that. Okay, so I'm going to mute Mike. Okay, so so I asked you to say it out loud, right? If you have a question, don't say it in the chat, say it out loud. I can't see the chat while I'm teaching, but someone's asking when the next exam is. So the third exam, right, so I announced that, right? So I announced that the third exam is on the 13th already, right? That was in last class. I think at the end of last class, I announced it. Right? So test 3, Okay, so test 3 is on May 12th. Okay, so test 3 is on May 12th. Okay, so during class. Okay. Okay, so, okay, no problem. So let's keep going. Okay, so we have the alternating series test. Okay, so let's look at an example. So here's an example using the alternating series test. Okay, so for example 1, we are going to see that the alternating harmonic series, which is of the form 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus dot dot dot, which you can write as equal to the sum from n equals 1 to infinity of the terms of the form -1 to the n minus 1 over n. Okay, so that's the harmonics. That's the alternating harmonic series. I'm going to underline it because it's important, right? The harmonic series is just adding 1 over n, right? 1 plus 1/2 plus 1/3 plus 1/4 plus dot dot dot. That's the harmonic series. The alternating harmonic series starts at 1, and it's the terms of the harmonic series, but you alternate between plus and minus. So it's 1 minus 1/2 plus 1/3 minus 1/4 plus dot dot dot. That's the alternating harmonic series. Okay, and so here in example 1, we're going to see that this series is convergent. Well, so first notice, so we notice that that the term, the b sub n terms are decreasing. And this is because, what are the b sub n terms? So 1 over n, right? So b sub n plus 1 is 1 over n plus 1. That's less or equal to 1 over n. Yeah, strictly less than. It's strictly less than 1 over n, right? So we have less or equal to because we have less than, right? So the n plus first, the b sub n plus 1 is 1 over n plus 1. That's strictly less than b sub n, which is 1 over n for all n. And so the b sub n terms are decreasing. See here, we want decreasing b sub n terms. Also, if you want to compute the limit, the limit as n approaches infinity of the b sub n terms, then what you'd be computing is the limit of 1 over n. Right? B sub n terms of 1 over n. So what's the limit of 1 over n? It's 0. So we have a and b. Okay. Also, why is the entire sum positive? Right. So we need, we have an alternating series. Put that. We have an alternating series, right? So that's good. Right? Because it's alternating between plus and minus here. Right? You see that? So we have an alternating series, check. The terms are decreasing, check. The limit of the b sub n terms is 0, check. The only thing left is that the entire sum is positive. So I'm asking, why is the entire sum positive? Well, just pair up the terms. If you look at 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus dot dot dot. Look at every consecutive terms. 1 minus 1/2 is positive. 1/3 minus 1/4 is positive. 1/5 minus 1/6 is positive. And so adding up these infinitely many terms is like adding infinite pair of terms where each pair is positive. So even though there's plus and minus, the positive term minus the next plus the negative next term is positive. And so you can think of this infinite sum of positive negative values as an infinite sum of positive values. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus dot dot dot. And so since you're adding the sum is an infinite sum of positive numbers, it's positive. Okay, so the entire sum can be thought of as an infinite sum of only positive numbers by pairing terms next to each other. Appropriate way. So the sum, you can see the sum. So you can see the sum as 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus dot dot dot. See, they're all positive. Okay, so the alternating harmonic series is convergent because it meets all the assumptions of the alternating series test. Okay? All right, and so the alternating series test is convergent because it satisfies all 4 of the conditions needed to use the alternating series test. And the conclusion is it converges. Okay, so that's example 1. So next is example 2. So example 2 is we want to show, so we want to study the convergence or divergence of the series, of this series. So the series is the sum from n equals 1 to infinity of the terms -1 to the n, 3n times 3n, over 4n minus 1. Okay, so we want to look at this series. Okay, so our first thought, let me put a solution here. Our first thought is to use the alternating series test because the terms are clearly alternating, right? So the first thought is to use the alternating series test because it is an alternating series. Okay, but we see quickly that we cannot apply the alternating series test to this example because the limit of the b sub n terms is not 0. If you take the limit of the b sub n terms, so if you take the limit of the b sub n terms, then you're taking the limit of this. So you want the limit of well, not the negative one, sorry. So the b sub n terms are without the negative here. So you're taking the limit of this, but what is the limit of that? If you divide by n in the numerator and denominator and calculate this limit, you get this is equal to the limit as n approaches infinity of, so divide the numerator and denominator by n, and so you get the fraction 3 over 4 minus 1 over n. Okay, so I just divide the numerator and denominator by n. And now if you take the limit of that, it becomes 3 over 4 minus 0. And 3 over 4 minus 0 is 3/4. But 3/4 is not 0, right? Okay, so condition B of the alternating series test fails. Here. The limit is supposed to be 0, but it's not 0 of the B sub n terms. And so even though it's an alternating series, you cannot apply the alternating series test. And so here you have to apply another reasoning here. Now, so what you can do is observe that the limit of the a sub n terms, which is the limit as n approaches infinity, the limit of the a sub n terms is the limit. These are the a sub n terms, right? These are the original terms of your series. This limit does not exist, okay? Because it's alternating between positive and negative. Okay. Now, as the limit as the b sub n terms approach infinity is 3/4, and so the absolute value of the terms is approaching 3/4, but it's alternating between plus and minus. And so as you go really far out into the terms of this series, you're getting terms that are pretty close to 3/4 minus 3/4, 3/4 minus 3/4, 3/4 minus 3/4. It's not exactly 3/4 and minus 3/4, but they're getting closer and closer. The odd and even terms are getting closer and closer to 3/4 and minus 3/4, one or the other, right? So you see, it's this the terms are going up and down, and so the limit does not exist, right? The limit of the terms does not have to be. I mean, it doesn't be 0. So the limit does not exist. So by the test for divergence, series diverges. Okay, the test for divergence said that, right? The test for divergence says that if the limit does not exist, then the series diverges, right? So we have that the limit does not exist. Okay, either the limit does not exist or the limit is non-zero, right? So if the limit does not exist, or if it does exist but it's not 0, then the series diverges. So here the limit does not exist, okay? So as a reminder, if the limit does not exist, or if the limit does exist as a finite number, but is not 0, then the series diverges by the test for divergence. Okay, and so since here the limit does not exist, by the test for divergence, this series diverges. Okay, and so your first thought again is that since it's an alternating series, apply the alternating series test. But you can see that the limit does not exist. Right, so the limit is non-zero of the b sub n terms, and so you can't use it. And so instead you use the test for divergence. Okay, example 3. Okay, and so I'll make a key point here. So the key point here is that even though you have an alternating series, sometimes in order to set up its convergence or divergence, you need to use another method other than the alternating series test. Right? Because there are 4 conditions, not just one. There's 3 other conditions other than it's an alternating series. Okay, so example 3 is test the series, test this series. Okay, so if I don't write the summation symbols, it's n equals 1 to infinity by convention. So this is the sum from n equals 1 to infinity, negative 1 to the n plus 1, times the fraction n squared over n cubed plus 1. So test the series for convergence or divergence. Okay, so Here, we just want to conclude whether or not the series converges or diverges. We're not trying to find the actual sum, okay? And remember, a convergence of a series means that the sum, right, the limit of the partial sums is finite, exists and is finite. That's what convergence means of a series, okay? Right, we defined a series in terms of partial sums, right? The sum of the first n terms, that the sum of the first n terms of your infinite sum, they represent terms of a sequence called the partial sum sequence, right? Sequence of partial sums. Okay, so we want to test that for convergence or divergence. Okay, so the given series is alternating, right? You see the -1 to n plus 1. So it's alternating between positive and negative. So the given series is alternating. So we try the alternating series test. Okay, so we think maybe the alternating series test can tell us whether or not the series converges or diverges. Okay, so I'm going to do something weird here. I'm going to let f of x equal to, I'm going to define a function, a continuous function f of x, and I'm going to let it be x squared over x cubed plus 1. Okay, so I'm going to define this function f. Here, f is a continuous function. Okay, so the terms a sub n and b sub n, right? They're terms of a sequence, right? The terms of the sum. Here, this is a function. This is a continuous function. Okay, but if you plug in a positive integer, the values correspond with the values of the sequence. So, for instance, so the values of f, positive integers, correspond with the terms b sub n of the given series, right? So what that means that, for instance, f of 1 is equal to b sub 1. Okay, f of 2 is equal to b sub 2. F of 3 is equal to b sub 3, and so on. Okay, so you can get all the terms of the sequence b sub n, these terms, b sub n terms, by plugging in positive integers into this function f I defined here. Okay, and so the goal is going to be to show, using calculus, specifically finding f prime, which is the derivative of f, to show using calculus that f is eventually decreasing as a continuous function, since the terms b sub n lie on the graph of f, showing that f is eventually decreasing means the terms b sub n are eventually decreasing. Okay, so eventually decreasing means that if you go far enough out into your sequence, all the terms from that point on are decreasing. Okay, a decreasing sequence, again, reminding you that it's a sequence that when you start at the beginning, the terms are decreasing, or always decreasing from the beginning. An eventually decreasing sequence is one where it may not be decreasing in the beginning, but if you go sufficiently far enough out into the sequence, it will then always be decreasing from then on. That's an eventually decreasing sequence. Okay, and so we can relax the conditions of the alternating series test to where instead of saying that the terms are always decreasing, we can say the terms are eventually decreasing. Okay? Because what the alternating series test really cares about is it's the sum of an infinite amount of terms. And when you add infinitely many terms, what finitely many terms do don't matter with regards to convergence or divergence, right? Is the sum finite or is it infinite? If you add a million of the terms, it doesn't matter how large those million terms are. It's a finite number, right? And so we don't need our sequence to always be decreasing. We just need it to be eventually decreasing. And then we can start at the point where it's decreasing and say, well, before that, we had finitely many terms, okay? So we can relax the conditions of the alternating series test to say, instead of saying the B sub n's are always decreasing, we can say the B sub n's are eventually decreasing. Okay, and so this problem raises the level of difficulty just a little bit, because now in this example, we don't have terms that are always decreasing. We don't have B sub n's that are always decreasing. We have B sub n's that are eventually decreasing. Okay. So this f function is going to be eventually decreasing. So let's do calculus to find the derivative of f, and then that will show that it's eventually decreasing. So f prime of x is the derivative of this, right? Now, you can use the quotient rule, right, which says that you take the bottom function, x squared, x cubed. You take the bottom function x cubed plus 1 times the derivative of the top function, which is 2x. Subtract the top function, which is x squared, times the derivative of the bottom, which is 3x squared. And then divide all that by the bottom function, x cubed plus 1 squared, right? Bottom times derivative of top minus top times root bottom over bottom squared. So this is by the quotient rule. Okay, so this is from last semester. Okay, so by the quotient rule, f prime of x is equal to that. So now we're going to just apply algebra to multiply and add common terms. And so if you multiply and add common terms, you get the numerator is 2x to the fourth plus 2x minus 3x to the fourth, and the denominator is still x cubed plus 1 squared. Okay, so this is by algebra. Okay, so this is multiplying out and then adding and subtracting common terms. Common terms mean terms that are both, x's or both x squares or both x cubes or both x to the fourths, right? It's adding common terms. Okay, so now, okay, so almost done. So I did in 2 steps here. So the 2x to the fourth minus 3x to the fourth. You have the 2x and it's minus x to the fourth over the same denominator, x cubed plus 1 squared. Okay, so 2x to the fourth minus 3x to the fourth is minus x to the fourth, right? Just like 2 oranges minus 3 oranges is negative 1 oranges. Or $2 minus $3 is minus $1. Okay, 2x to the fourth minus 3x to the fourth is minus x to the fourth. Okay, and so now you factor the numerator and you get x times 2 minus x cubed. And the denominator is x cubed plus 1 squared. Okay, so now I've found f prime of x and I've written it in a convenient form. And so let's make the an observation. So f prime is negative when 2 minus x cubed is negative. Okay, x cubed plus 1 squared is always positive. As long as it's not 0, when you square something, when you square a real number, it's positive. So the denominator is positive. X, here, f, we're only thinking of positive x, right? So here, let f of x equal this, where x is positive, okay? So x is positive, and so 2 minus x cubed determines the sign of f prime of x because everything else is positive. Okay, so when 2 minus x cubed is negative, that means all of f prime is negative. So f prime is negative when 2 minus x cubed is negative. Okay, and so that's when, so 2 minus x cubed is negative when x is strictly greater than the cubed root of 2. Okay, so 2 minus x cubed less than 0 means x cubed is greater than 2. That means x is greater than the cubed root of 2. Okay, so f prime is negative when x is greater, strictly greater than the cubed root of 2. Okay, looking at f prime tells you the behavior of f. If f prime is negative, if the derivative is negative, that means that the function is decreasing. Okay, so that tells us that f is decreasing when x is greater than the cubed root of 2. Okay, so f is decreasing when x is greater than the cubed root of 2. So the cubed root of 2, right, is between 1 and 2, right? So note that if you take the cubed root of 2, it's something smaller than 2, right? It's not 1. 1 cubed is 1. And so this number, the cubed root of 2, 1 is strictly less than it, and that's strictly less than 2. So the cubed root of 2 is strictly between 1 and 2, okay? So we can conclude that f is decreasing when x is greater than or equal to 2, okay? So it's decreasing when x is greater than a number strictly between 1 and 2. Okay, and so that means it's decreasing when x is greater than 2. We want this number 2 because the positive integers, f maps the positive integers to terms of the sequence b sub n. And so knowing f is decreasing when x is greater than 2 means that f is decreasing when the input is an integer greater than 2. That means that the sequence, b sub n is decreasing for n greater than 2, right? Because the values of the sequence b sub n are the values of f when f is a positive integer, right? And so if f is always decreasing for x greater than 2, that means the terms b sub n on its graph are decreasing for n greater than 2. Okay, and so we call that eventually decreasing. And so b sub n is eventually decreasing. Okay, and so this verifies the relaxed condition, the relaxed condition 1 of the alternating series test. Okay, when you relax the condition on a theorem, it's when your original theorem has conditions, but you can assume, you can take the assumption and maybe weaken it a little bit, just enough so it still works, but it applies, it's something you can show in the problem you're working on, okay? And so important fact, okay? You can weaken condition 1 of the alternating series test to instead say that, the fact that the b sub n terms are eventually decreasing. Okay, or in other words, other mathematical words, b sub n plus 1 or in other words, b sub n plus 1 is less or equal to b sub n for all n greater or equal to capital N for some capital N. Okay. Put the quotations around it. Okay. Put the quotations go in the right direction. There we go. Okay. And so we're relaxing condition 1 on the alternating series test. And we showed it works here. Okay. Condition 2 is easily verified. Condition 2 is that the limit of the B sub n terms is 0. So the limit of the B sub n terms as n approaches infinity is equal to the limit of the terms of the sequence, right, which is this. And well, what's the limit of that? It's the limit where you can divide the numerator by n squared and the denominator by n squared. You get 1 over, divide the numerator by n cubed. You get 1 over n divided by 1 plus 1 over n cubed. And if you take the limit of that, you get 0 over 1 plus 0, which is 0. Okay, so we have that the limit is 0. Okay, so since the entire sum is positive, so why is the entire sum positive? Well, remember the terms are eventually decreasing. And we start with a positive value. So when n is 1, you get 1/2. When n is 2, you get 4/9, right? So a sub 1, -1 to 1 plus 1 is -1 squared. This is 1. So you get a sub 1 is 1/2. A sub 2, you plug in 2, and you get negative, you get 4 over 9, -4/9, right? A sub 3, you plug a sub 3 in, it's positive here, and you get 9 over 28. So just like earlier where you can cancel terms, we showed that it's a decreasing for n greater or equal to 2, the B sub n's, right? So that means that the positive, the absolute value of the terms is decreasing. So 9/28 is less than or equal to 4/9, right? And so forth. Okay, but you can pair it up this way. Your sum is basically 1/2 minus 4/9 plus 9 over 28, and then minus, and if you plug in 4, you get 16 over 65 plus ... right? But just pair up the terms like we did earlier. This is the same as 1/2. This is the same as 1/2 minus 4/9 plus 9/28 minus 16/25 plus ... right? Where each pair, each consecutive pair of terms add up to a positive number. Okay, so this is positive plus this positive plus ... So the entire sum is positive. The entire sum is positive. It's eventually decreasing. The limit is 0. The entire sum is positive. Okay, and so let's quickly. You have an alternating series. So we have, well, the timer sum is positive, eventually decreasing, and the limit is 0. And you have an alternating series. Okay, right? Okay, and we have and alternating series. I have said that earlier already. Okay, so since all four conditions, since all four required conditions of the alternating series test are met, the given series converges. Okay. And by the alternating series test. Okay, so then that theorem is done. So let's look at another theorem. And this is called the alternating series approximation theorem. Okay, so if S, which is equal to the sum of -1 to the n-1 of b sub n is the sum of an alternating series that satisfies the following. One, that 0 is less or equal to b sub n plus 1 less or equal to b sub n. 2, and 2, the limit as n approaches infinity. Limit as n approaches infinity of b sub n is 0, then the absolute value of r sub n, which is equal to the absolute value of s minus s sub n, is less or equal to b sub n plus 1. Okay, so this is called the alternating series approximation theorem. So I'm just gonna, there we go, section that off there. Okay, we're calling S the entire sum. And it's the sum of an alternating series. And also notice that the power of n of -1 is n minus 1, right? And we're starting at n equals 1. And so that means that the first term is positive. -1 to the 1 minus 1 is -1 to the 0, which is 1. So this is an alternating series that starts with a positive number. Okay, so S represents the entire sum. And so we have this sum that satisfies that the terms, the b sub n terms are non-negative and decreasing, and the limit of b sub n terms are 0. Then we can say that the absolute value of the difference between the entire sum and the sum of the first n terms is at most b sub n plus 1. Okay, what does that mean? That means that if you want to approximate the entire infinite sum, the conclusion is telling you that the entire infinite sum represented by the real number s, the distance between that real number and the sum of the first n terms, the absolute value of the distance between those two real numbers is at most the b sub n plus 1 term. Okay, so let's look at the whiteboard. So what's happening is that if you have the real line, this is a straight line. If you have the real line, s is a real number on that line. S sub n is the sum of the first n terms of right? So you have an S sub n. S sub n is the first sum of the first n terms of your infinite sum. You have b sub n plus 1, which is just the absolute value of the n plus first term. The conclusion of the theorem is saying that the distance, So what we also have is the absolute value of s minus s of n, right? This is the distance between s of n and the real number s. And so let's look at b sub n plus 1, right? The conclusion is saying that this is less than or equal to b sub n plus 1, which is a non-negative number. So what that means is if you took kind of an open bowl here of radius b sub n plus 1, right? So this would be s plus b sub n plus 1. This would be s minus b sub n plus 1. Then the radius of this guy is b sub n plus 1. So the length of this and the length of this, they're both b sub n plus 1. Okay? So the length of those two halves is the positive value b sub n plus 1. And so the conclusion theorem is saying that s sub n, okay? Sorry, s sub n is a real number. And so what you're saying is that the number s sub n, which is this guy, here's s sub n, right? It's saying that the real number s sub n, which is here, if you look at the raised b sub n, that means s is somewhere in this interval. Okay? So let me use green here. The real number s, which is the sum, is somewhere here. Okay? S is somewhere here. Okay? And I'm going to have to include the s sub n here. This is s sub n. So if you start s sub n here and you add and subtract b sub n plus 1, s, which is the actual sum, is somewhere in this interval from s sub n minus b sub n plus 1 to s sub n plus b sub n plus 1. That entire sum s lies here. So this is an approximation of the entire alternating series, because what you're doing is you're saying the entire infinite sum s, real number s, has to be somewhere in this interval. And the smaller you make b sub n plus 1, the smaller this interval gets, and the more you're restricting where the entire sum, the value can be. Okay, it can only be here. It can't be outside of it. And so we are approximating the sum by saying it's somewhere in here. Okay. Okay, so let's go back to here. Okay. So that's the alternating series approximation here. So let's look at example 4. Find the sum of the series so it's the sum starting at n equals 1. I mean, starting at n equals 0, so I'm going to write that in. N equals 0 to infinity. -1, the n, over n factorial. So find the sum of that series correct at 3 decimal places. Okay, so in this example, we can take the sum from n equals 0 to infinity of -1 to n over n, and we're going to find the sum correct to 3 decimal places. Okay. And note that 0 factorial is equal to 1. Okay. Okay, so solution. So we observe that the sum of the series is convergent by the alternating series test. Because b sub n plus 1, which is equal to 1 over n plus 1 factorial, which is equal to 1 over n factorial times 1 over n plus 1. Put parentheses here just so that you can see that. That's strictly less than 1 over n factorial, which is equal to b sub n. Okay, the b sub n terms are 1 over n factorial, right? So b sub n plus 1 is 1 over n plus 1 factorial. And so n plus 1 factorial is n factorial times n plus 1. And so that's equal to 1 over n factorial times 1 over n plus 1. But 1 over n plus 1 is a proper fraction. It's a positive number strictly less than 1, right? When n is 1, you get 1/2. When n is 2, you get 1/3. When n is 3, you get 1/4, right? So this is 1 over n factorial times a proper fraction, which means that it's less than 1 over n factorial, right? 1 over n factorial times 1/2 is less than 1 over n factorial, right? So taking half of 1 over n factorial is less than 1 over n factorial. Taking 1/10 of 1 over n factorial is less than 1 over n factorial. Okay, so then the b sub n plus 1 term is strictly less than b sub n. And so the b sub n terms are decreasing. Okay, also, so this is condition 1. So I'm going to put a 1 here. Okay, so 1 is because condition 1 is satisfied. Condition 2 is that the limit is 0. Well, notice that 0 is less than 1 over n factorial, which is less than 1 over n by very similar reasoning. 1 over n factorial in the denominator multiplying the positive integers from 1 to n. And so 1 over n factorial is really 1 over n times a bunch of proper fractions, right? And so 1 over n factorial is really taking 1 over n and making it smaller. And so 1 over n factorial is less than 1 over n. Okay, so that's true, but then see that the n terms, the limit of 1 over n, the limit of 0 is 0. And the limit of 1 over n is 0. So the limit of the n things here is 0, and 1 over n factorial is sandwiched between them. And so if the terms of a sequence are sandwiched between two sequences whose limit are 0, right, that means that the in-between limit is 0. Okay, so that implies that the limit of b sub n, which is 1 over n factorial, is 0. Okay, so we have condition 1 and condition 2 met. We also know that the first, it starts n equals 0. That way the first term is positive. And so since the b sub n's are decreasing, it's alternating between positive and negative, and the first term is positive, you can just add consecutive terms. b naught minus b1 is positive. b2 minus b3 is positive. b4 minus b5 is positive. So the entire sum is really b naught minus b1 plus b2 minus b3 plus b4 minus b5 plus dot, dot, dot. Since the first term b naught is positive, all the terms are positive, and so the entire sum is positive. Okay, all the sum of consecutive terms is positive, okay? Okay, so the entire sum is positive. We have these two, and it's alternating. And so by the alternating series test, we see it's convergent, okay? So all four conditions of the alternating series test are met. Not just those two, okay? It's an alternating series, and the sum is positive. Okay, so we know the series converges. Okay, so now we want to see how many terms we need to find the sum correct to 3 decimal places. So let's just do some calculations and find add up some of the terms. Okay, so S, which is the entire sum, is equal to the first term, 1 over 0 factorial, minus 1 over 1 factorial, plus 1 over 2 factorial, minus 1 over 3 factorial, plus 1 over 4 factorial, minus 1 over 5 factorial, plus. And so what that's equal to is 0 factorial is 1. 1 over 1 is 1. This is 1 minus 1 plus 1/2 minus 1/6. Right? 3 factorial is 3 times 2 times 1. That's 6. That's minus 1 over 6 plus 1 over 24. 4 factorial is 4 times 3 factorial. 3 factorial is 6. 4 times 6 is 24. That's minus 1 over 5 factorial, which is 1 over 120 plus that. So 5 times 24 is 5 times 20 plus 5 times 4. That's 100 plus 20. 120. So it's plus that. Okay, so this is the entire infinite sum. Okay. So we also see here that the b sub n terms. b naught is 1. b1 is 1. b2 is 1/2. b3 is 1/6. b4 is 1 over 24. b5 is 1 over 120. Okay. So notice that b sub 7 is equal to, okay, so let me write out a few more terms here. So this is plus 1 over 6 factorial minus 1 over 7 factorial plus ... So plus 1 over 6 factorial, that's 1 over 6 times 120, which is 720. That's minus 7 times that, which is 5,040. 1 over 5,040. Okay, plus ... So then 7 times 7 is 7 factorial is 6 factorial times 7. So 7 times 7 is 49. That's 4,900. 7 times 20 is 140. 4,900 plus 140 is 5,040. Okay, so you have that plus that. Okay, so b sub 7 is the absolute value of this last term here, the 1 over 7 factorial, the negative. So this is b naught, b1, b2, b3, b4, b5, b6. b7 is 1 over 5,040. This is 1 over 5,040. And so that's strictly less than 1 over 5,000, right? If you make the denominator smaller, larger, the fraction is smaller. If you make the denominator smaller, the fraction gets larger. So 1 over 5,040, which is b7, is strictly less than 1 over 5,000. 1 over 5,000 is 2 over 10,000. So that's 0.002. That's 2 10,000ths. So b7 is strictly less than 2 10,000ths, 0.0002. Right, the first decimal place is tenths, hundredths, thousandths, 10,000ths, 2 10,000ths. Okay, so b7 is strictly less than 2 10,000ths. We want to correct the 3 decimal places. The 2 is in the 4th decimal place here. Okay, so notice that b7 is strictly less than that, and s sub 6, which is the sum of the first, well, s6 ironically is the sum of the first 7 terms, because it starts at b naught. So b naught to b6 is 7 terms. So s sub 6 would be this, starting at the 6, ending at the 6 factorial here. S sub 6 would be b naught minus b1 plus b2 minus b3 plus b4 minus b5 plus b6, and you stop. That's s sub 6. Okay, and so if you do all of that, you get that this is approximately equal to, you get that's approximately equal to 0.368,056. And so in this example, we're lucky because it works out well, that because there's a 0 in the 10,000ths place. See that 0 there? That 0 there is helpful. We can see that sometimes if the rounding doesn't work out, we actually have to go further out into the sequence in order to get the first 3 decimal places right. But I'll show you, go further. So S sub 6 is approximately 0.368056. Okay. By the alternating series estimation theorem, approximation theorem, estimation, approximation theorem, we use the same word. We know that the absolute value of S minus S sub 6 is less or equal to B sub 7, right? The conclusion of the theorem is that the absolute value of the sum minus S sub n is less or equal to B sub n plus 1. So the absolute value of S minus S sub 6 is less or equal to B sub 7. B sub 7, we saw, was strictly less than 0.0002. Okay. So what this means is that the error of S sub 6 in approximating S is less than 0.0002. Okay, because the absolute value of S minus S sub 6 is strictly less than 0.0002. So that means that S sub 6 is at most is less than 0.0002 away from the actual value, to the right or left, right? It could be more or less than that amount. Okay, so the error is less than that. Okay, and so if you look at a range of values, if you look at 0.368056, right? And if you look at so there's a final. Okay, I'll talk about that at the end of the class. Okay, so okay, so here this number. Okay, so you have that's the value. Oh, this is what I want to insert symbol. Oh no, just do it myself. Okay, so if you were to add 0.0002 to that number, you would get 0.368256, right? Okay, now if you were to subtract that same amount, then previously you'd subtract 0.0002, and so you get 0.367856. Okay, so what's happening here is that you're subtracting. This is minus. This is minus 0.0002, and this is plus 0.0002. Okay, so this is S sub 6 here, right? And so we know that the error is less than 0.0002. If you add or subtract 0.0002, you see that even though the first 3 decimal places change here, you would round up to 0.368. And so what that's saying is that then the first three decimal places you could say are 0.368. Okay, so you'll have to do that. Okay. Okay, so that means we have that S is approximately, this is the approximately symbol, that squiggly squiggly sign there. S is approximately 0.368, correct to 3 decimal places. Okay, correct 3 decimal places after rounding. Okay, after rounding. Okay, because you can see that we've shown here that if you add or subtract this 0.0002, after you round, the first 3 decimal places has to be 0.368. All right. Okay, so we have that situation. And so the next conversation is about absolute convergence. Okay, so this is another important topic here. Okay, so given any series, the sum of a sub n, we can consider the corresponding series, the sum from n equals 1 to infinity of the absolute value of a sub n. And so that's equal to the absolute value of a sub 1 plus the absolute value of a sub 2 plus the absolute value of a sub 3 plus the absolute value of a sub 4 plus that. Okay, so given an original series, instead of thinking of the original sum, we can think of the sum of the absolute values of the terms of that sum. Okay, this is whose terms are the absolute values of the original series. Okay, so the terms are the absolute values of the original series, of the terms of the original series. Okay, definition. Okay, a series the sum of a sub n is called absolutely convergent if the series of absolute values, which is the sum, which is this sum. But I'm going to write this, which is the sum of the absolute value of a sub n if that series is convergent. Okay. Okay, so the series is called absolute convergent if the series of absolute values is convergent. So let's look at this example 5. So the series, which is the sum from n equals 1 to infinity of -1 to the n minus 1 over n squared is equal to 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus dot. Okay, so you have that series. And so this series is absolutely convergent because with the absolute value of the terms, right over here. And so that's because if you take the original series, right? But now you're going to take the absolute value of the terms. Right, so now you take the absolute value of the terms, and now the negative one is gone. Right, the negative one is gone because you're taking the absolute value, so you get that, right? And so now this is the absolute values of these terms. Well, this term is convergent because it's a P series, right, where P is 2. So this is convergent as a P series where P is equal to 2, which is strictly greater than 1, right? So reminder, a P series is convergent if and only if if P is greater than 1. Okay, and also a reminder what a P series is. Reminder, a P series is a series of the form. So if you have a sum from n equals 1 to infinity, 1 over n to the p, right? That's a P series. Okay, and so here it's a P series where P, the exponent of n, the denominator is 2, and it converges if P is greater than 1, 2 is greater than 1. So it's convergent P series, right? And so now the sum of the absolute value of the terms is convergent, and so that means the series is absolutely convergent. Okay. Okay, example 6. Okay. The alternating harmonic series is not absolutely convergent. Okay, so I'll show you why. So if you take the sum of the alternating harmonic series, just over n. Okay, so that's the alternating harmonic series, right? It's equal to, when n is 1, you get 1 over 1. When n is 2, you get minus 1/2. When n is 3, you get plus 1/3. When n is 4, you get minus 1/4. Plus that. That's the alternating harmonic series. But if you take the sum of the absolute values of its terms, right, if you look at the sum of the absolute value of the terms, then what you get is this is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus ... Okay, and that's divergent. And so this is divergent as the harmonic series. Not the alternating harmonic series, it is the harmonic series, which is a P series in which P is equal to 1. Right? The exponent in the denominator is 1. Right, such that P equals 1. Okay, so the series is not absolutely convergent because if you take the absolute value of the terms, if you add them, you get the harmonic series, which is divergent. Okay. Okay, so let's look at something else. Another definition. A series, the sum of A sub n is called conditionally convergent if it is convergent, but not absolutely convergent. Okay, so a series is called conditionally convergent if it is convergent, but not absolutely convergent. Okay. So we can see from example 6 that the alternating harmonic series is not absolutely convergent. We saw before the alternating series test that the alternating harmonic series was convergent. Okay, so the alternating harmonic series is not absolutely convergent, but it is convergent. That means the alternating harmonic series is conditionally convergent. Okay, so this is an important example to keep in mind. The alternating harmonic series is conditionally convergent. It's convergent, but not absolutely convergent. Okay, and so this proves the existence of a conditionally convergent series, right? So we gave a definition of a conditionally convergent series, but it doesn't have to be true that any series satisfied that definition or that there was any series that was conditionally convergent. But here, the alternating harmonic series is conditionally convergent, and so we proved the existence of such a series. Okay, so another theorem. If a series sum of a sub n is absolutely convergent, then it is convergent. Okay, so the theorem is telling you that if you show a series is absolutely convergent, then it is convergent. Okay, so let's look at an example. Example 7. Determine whether the series, the sum n equals 1 to infinity of the terms cosine n over n squared, determine whether that series is convergent or divergent. I'm just going to write some of the terms. This is equal to cosine something over this. Okay, so just copy this. Okay, so this is cosine of 1. This is cosine of 1 over 1 squared plus this is cosine of 1 over 1 squared plus cosine of 2 over 2 squared plus cosine of 3 over 3 squared plus dot, dot, dot. Okay, so determine whether that series is convergent or divergent. Okay. Okay, so this one's a little different. This series has positive and negative terms, but it is not alternating. Okay, so cosine of 1 is right? So the cosine graph goes up and down like a wave, right? It goes above the x-axis, below, then above again, then below. So if you do cosine 1, cosine 2, cosine 3, dot, 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 it will alternate between, some will be positive, some will be negative, but it will not be alternating, right? It will not always be positive, negative, or negative, positive, negative, positive. Okay, so there won't be that pattern of positive, negative terms. Some will just be positive and some will be negative. So it's not an alternating series. Okay. Okay, so the first term is positive, the next three are negative, and then the following three are positive. So the signs are changing irregularly. Okay. So what we can do is we can apply a comparison test to the series of absolute values. Okay. So if you take the sum, this is your original series. If you take the sum here, but you think of the sum of its absolute terms of the absolute values, you take the sum of the absolute value of the terms, right? This is equal to the sum where the absolute value can move to the numerator, because the n squared is always positive for n greater or equal to 1, right, as integers. Okay, so this is now the sum of the absolute value of the terms. Now we know that we know that the absolute value of cosine of anything, specifically cosine of n, is less or equal to 1 for all n. And so since that's true, since we have that inequality, that equality applies for all the terms. And so that means that the absolute value of cosine n over n squared, this thing, is less or equal to the fraction where the numerator is now 1 and the denominator is still n squared. Okay, so you can see that this is less or equal to that for all n. And so if you replace this numerator with 1, you're getting something greater than or equal to 1. So you have this relationship here. We know that the sum okay, so we know that that sum is convergent, again, as a p-series, where p is equal to 2, which is strictly greater than 1. Okay, so we now know that the sum of these terms is less or equal to the sum of these terms, which is convergent. Okay, by the comparison test, we conclude that the given series is absolutely convergent, because the series of its absolute value terms, this series, is convergent. Okay, so right, the sum of the absolute value of the terms is less or equal to the sum of these terms, and that sum is finite, and so this sum is finite, converges. So this being convergent means the original series is absolutely convergent. Okay, so what we showed is that this series is absolutely convergent. Okay, by a theorem, the original series, this series, is convergent. The original series is convergent, right? And so we had the theorem. I'm going to put an underline here so that it stands out. This theorem, if a series is absolutely convergent, then it's convergent. So we showed us that this series is absolutely convergent. And by that theorem, that means the series is convergent. Okay? Okay, so that's good. Next is the ratio test. Get rid of the underline. Okay, so the ratio test is 3 parts. if the limit as n approaches infinity, the absolute value of a sub n over a sub n plus over a sub n plus 1 equals L, which is strictly less than 1, then the series of the summation of a sub n is absolutely convergent. Right? And the series being absolutely convergent means it's convergent, right? Okay, you know what? I'm going to put in this n equals 1 to infinity there. So this is the sum from n equals 1 to infinity of a sub n. Okay? So then that series is absolutely convergent. That's if the limit of the terms a sub n over a sub n plus 1 is L, a finite number, which is less than 1. Okay? Then the series is absolutely convergent. 2, if the limit, which equals L, if the limit equals the number L, but it's greater than 1, or the limit, instead of equaling a real number L, is equal to plus infinity, then the series, this series is divergent. Okay, and 3, if this limit is equal to 1, the ratio test is inconclusive. That is, no conclusion can be drawn from the ratio. Remember, from the ratio test doesn't mean it's impossible. It just means from this test. From the ratio test, no conclusion can be drawn from the ratio test about convergence or divergence of the result of the same series. We're talking about this sum here. I hope this fits. Yes, it does. Good. Okay, so that whole thing is the ratio test here. This parts 1, 2, and 3. And so the limit of this, the limit of absolute value of a sub n over a sub n plus 1, if it's a finite number less than 1, this series is absolutely convergent. If it's a finite number greater than 1, the series is divergent. If the limit is 1, then you draw no conclusions from this test. Okay? That's the ratio test. This is another way to determine whether or not a series is convergent or divergent. Okay, so let's look at example 8. Example 8. Test the series, the sum for n equals 1 to infinity of -1 to the n of n cubed over 3 to the n. So test that series for absolute convergence. Okay, solution. Okay, so we use the ratio test with a sub n equal to these terms here, the terms in the sum. Okay, those are going to be the terms. And so now we're going to look at the value of the absolute value of a sub n over a sub n plus 1. Okay, and so then that's equal to So in the numerator, we have a sub n. Right? So it's the absolute value of it, though. So we're going to have the absolute value sign here. And then denominator, we're going to have the absolute value, but we're going to have the absolute value of negative 1 to the n plus 1. And then this is n plus 1 cubed over 3 to the n plus 1. Simplified. Okay, so now this is Ben. Yes?
In the textbook, it says a of n plus 1 over a of n.
Oh, that's just a typo. Okay. A sub n plus 1 over a sub n. Okay, thank you. I wrote. Oh, right. Oh, okay. Oops. Okay. It's a typo. It's a sub n plus 1 over a sub n. Don't know why I wrote the other one. It's a sub n plus 1. Okay, so it's just the limit of this. Limit of a absolute value of a sub n plus 1 over a sub n. Okay. So now we're going to look at that term, and then we're going to look at its limit. So if you take the absolute value of that, you then simplify that. So if you simplify that, you get oh, okay. I gotta fix this now. This is n cubed 3 to the n. This is now n plus, this is an n here. This is for the n term. This is for the n plus first term. This is for the n plus first term also. All right, so I'm just making the n plus 1 term in the numerator and the n term in the denominator. Okay, so if you take the absolute value of that, you're going to get an n plus 1 cubed for this n plus 1 here. This is a 3. Okay, so then you're going to take that term and divide it by 3 to the n plus 1. That's the numerator. And then the denominator is just n cubed over 3 to the n. And those are all 3's. It's on A. So then this is equal to the fraction. The fraction of the numerator is just stays as it is. But if you divide, you get that. But then if you divide by a fraction, it's the same as multiplying by its reciprocal. So this is 3 to the n over n cubed. Okay, so dividing by the fraction n cubed over 3 to the n is the same as multiplying by 3 to the n over n cubed. Okay, and so then this is equal to, this is then equal to the fraction n plus 1 over n cubed. Okay, and then times, so 3 to the n over 3n plus 1 is 1/3. You just subtract the exponents, n minus, in parentheses, n plus 1, negative 1. 3n over 3n plus 1 is 1/3. Okay, so you get that. Okay, and so then this is equal to 1/3 times 1 plus 1 over n cubed. So I just, n plus 1 over n is 1 over n, 1 plus 1 over n. You divide n plus 1 by n, you get 1 plus 1 over n. So you cube that. But now if you take the limit of that, as n approaches infinity, then the 1 over n just goes to 0. So you just get 1/3. This thing becomes 1. If you take the limit of this, it becomes 1 plus 0 cubed, which is 1 cubed. And this is still 1/3. 1/3 times 1 is 1. So that limit is 1/3, which is strictly less than 1. So what we showed, we just showed that the limit of this guy is a finite number less than 1. Okay? I'll get rid of the is less than 1. Okay? And so thus, by the ratio test, the given series is absolutely convergent and therefore convergent. Okay, so the given series is absolutely convergent and therefore convergent. Okay, so just stay with me a few more minutes. I'm going to finish this section and then we'll end class. So I'm just going to make an important okay, so I'm going to make an important announcement. Okay, so so the final, right? So the final, so I want to make the final a little day of class, which is on 5/17/2021. Okay, so I want to make the final that day, and so I just have to check with the department to make sure that that's okay. Okay, and so okay, so on Wednesday I will confirm. So on Wednesday I will confirm at the final, the day of the final. Okay. Okay. So the plan is to make it the last day of class, the 17th. Okay. So if the department doesn't mind, they usually don't. I've asked this before. And so if they don't mind, I'm going to make it the 17th. And so it will probably be the 17th. Okay. So I'll tell you for certain on Wednesday if it's on the 17th or it isn't. Okay. So be prepared. And so I'm going to make a review sheet for you and you'll have the review sheet. It will be up by Wednesday. Okay. Okay. So the review sheet for the final will be up by Wednesday. Okay. But it will probably be up sooner. Okay. 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 So remember the third test, test 3 is on the 12th. And a reminder, I already accept this. Test 3 is on the 12th. So it's 5/12/2021. So that is the second to last day of class. Okay. The 12th is on the second to last day of class. It's a Wednesday, which is Wednesday. Okay. Okay, that's definite. Okay, that test 3 is on that day. And so I'm going to check with the department and then I'll tell you for certain next class. Okay, that about the final date. Okay, and the review sheet will be up by Wednesday online. Okay. Any questions about the final or the third exam? Say it out loud, please, because I can't see the chat while I'm doing this. The Zoom is also not letting me see the chat. I'm clicking chat and it's not popping up. So I can't, for some reason, I can't see the chat right now.
Professor, how about the review sheet for test 3?
What?
The review sheet for test 3.
Oh, right. Okay. So let me. Right. So it's up. It's already up. I put it up last week. I put it on.
Okay.
Let me hold on. I'm going to stop the share for a second because I'm going to sign into Blackboard. I'll show you where you can find it. Okay. So I announced the exam last week, test 3, and I had the I put up the.
So basically, to cover the whole chapter 8, right?
So it's only, yeah, it's only chapter 8. It's, I'm going to put it up on the screen for you to show you. Okay, good. Tests, test 3. Yeah, okay, good, it's here. Okay, so I'm gonna put this on the screen. Okay, so here's Blackboard, right? For our class, if you go to tests here, go to tests, you go down to test 3, right there, and there's the review sheet, right? And you click that, you open it. Okay, and so now this pops up. Okay, so that's the review sheet for test 3. These are examples from each section. So we'll finish the sections in time, and then these will be the review problems for the exam. Okay?
Thank you, Professor.
You're welcome. Okay, so I'm going to stop the share again for a second. Now I'm going to put it right back up. Okay, so I just want to finish quickly this section. Okay, so give me a few more minutes. So this is example. Okay, so now let's look at what's called the root test. So 1 on the root test, if the limit as n approaches infinity of the nth roots of the absolute value of a sub n is equal to L, which is less than 1, then the series is absolutely convergent. And therefore convergent. Once the series is absolutely convergent, it is therefore also convergent. For 2, if this limit which equals L is greater than 1, or the limit is equal to plus infinity. If the limit is greater than 1 or infinity, then the series of then the series is divergent. Okay, so if this limit is less than, it exists as less than 1, then this series is absolutely convergent and therefore convergent. If this limit is exists but it's greater than 1, or if the limit is infinity in the series, then that series is divergent. And 3, if you have this limit is equal to 1, the root test is inconclusive. Just like before, if you get this is 1, if you get this limit as 1, the test is inconclusive, and you draw no conclusions from this test. Okay, so one more thing, example 10. We're done with this section. Example 10, test the convergence series, the sum from n equals 1 to infinity of (2n plus 3 over 3n plus 2 raised to the nth power. Okay, so test the convergence of that series. That's example 10. Solution. Okay, so solution is first, let's look at the terms a sub n of this series. And they look like this. Okay, that's a sub n. Now, if you take the nth root, if you take the nth root of the absolute value of a sub n, that equals to, well, if you take the nth root of the absolute value, the n's cancel and you just get this fraction. You get that, right? But then that's equal to dividing the numerator and denominator by n, because n is the largest power of n, the denominator. You get 2 plus 3 over n over 3 plus 2 over n. And so then if you take the limit of that, then the 3 over n, 2 over n becomes 0, and you get 2/3, which is less than 1. Okay, so if you look at the root test, you see you're getting case 1. Okay, so thus the given series is absolutely convergent by the ratio by the root test. Right, by the root test, it's telling you the series is absolutely convergent. Okay, and then thus, so that means the given series is convergent. Right, by the previous theorem, if you have an absolute convergent series, then it's convergent. Okay, and so that is the end of 8.4. Okay, and so for homework, I want you to do okay, so for homework, I want you to do 8.4 homework, which is homework 21. So we finished 8.3 today. We finished 8.3 today, which means that you can also have that. So it's homework 20 and homework 21. So for homework, it's homework 20 and 21. Okay, due next class. Okay. Any questions about previous homework? Okay, so anyone have questions about the homework? Previous homework assignments? Any previous homework assignments? You want me to go over anything? So I'm going to stay for a little longer if you do. So anyone have any questions about the homework? Okay, so then I'll see you next time. Okay, so then I'll see you on Wednesday. Spell Wednesday correctly. Okay, and that's the end of class. Okay, so next class we will talk about the homework and we'll go over 8.5 and keep going. Okay, bye everybody. See you on Wednesday.
Bye, bro, sir.
Bye. Thank you for coming. Right, remember the review sheet is online for test 3 already. It's on the Blackboard website. Okay, bye everybody.